have a toy or anything? Yeah. Think I have one. She's tired too. She doesn't want to play. She's always got some kiss marks around her. Aww, Pinksy. So cute. Oh, her legs. Okay, can you start? Can you study? Oopsie. Okay, we're done. We're done. We're gonna start studying now. Okay, walk in, Pixie. Your future depends on this. So, our quiz tomorrow is based on one assignment. And that one assignment is based on oops, but I'm not showing my screen. I was just find my I have so many tabs open. I'm not usually like that. It's just yep. TCR8. That's what it is. She's so bored she's waking up Yuki. Oh my god, she's biting him. Got a 40% my first exam. It's okay though, right? Like right? I mean, I don't know. Yo, Max Powell, welcome. Welcome to the stream. I'm just kind of appalled by this score. Have fun. Question 5, I got nothing. Okay, whatever. We'll look at that later. First, we got to study. All right, so what we're trying to do is to find the largest open set U on which f of z is analytic, and to show that f prime z is equal to lowercase f of z on U. Capital F is just the integral of f, which is the derivative of that integral, right? Where f of z is the integrand. Then, for the given line segment C, explain why the fundamental theorem of calculus applies and use it to compute f of z, integral of f of z dz, or explain why it does not apply. So for this example, we have the exponent of z dz with c being z equals it, and 0, t is between 0 and pi, and f of z equal to the exponent z plus 2 plus I. Yo, Miguel and Italy and Layla Bowery, welcome to the stream, guys. How's it going? Show a little bit what I'm doing here. Oh, my cat's in the back. Let's turn the light on, even though it's morning here. You good? I don't know. I hope I am. I really do. I'm not though. I have to be. It's hard to say. But here's the solution, right? The function f of z is this. Exponent z plus 2 plus I, right? As it was mentioned here. This is z right here, not 2. This is our f of integrand f of z, like the capital F of z, is entire. We know it's entire because entire means analytic everywhere, right? Exponents are analytic everywhere. Plus 2 plus I, that's analytic everywhere. So it's entire. So U is complex, right? What does that mean? It's complex. And f prime z is equal to exponent z plus 0. Right, because the constants become 0 when you take the derivative. Exponents stay the same. So we know that f prime z is equal to the exponent z plus 0, which is equal to f of z on u. So since the c is a line segment from 0 to I pi, which is contained in u, picture below, the FTCC applies, fundamental theorem of complex calculus applies, and the exponent z is equal to f of z dz. And then we apply the complex, the fundamental theorem of complex calculus, and then we plug in I pi and 0, and then we simply get exponent I pi and exponent 0, which is equal to 1, right? Or negative 1, because of this negative sign. So e to the I pi is also negative 1. So negative 1 minus 1 is equal to negative 2. So that's our answer there. So we just have to look at where it's analytic. Miguel, Max Powell, Italy, Layla Bowery, are y'all there? Let me just save it first. A lot of miscellaneous stuff. All right. So yeah, exponent z is just the way to write it, but really it's just e to the z. You just you're just doing this, right? This is really complicated. So if we were to simplify, just e to the z dz. So the derivative is just e to the z. So that's f of z, and works everywhere. So u equals c. But what does it mean u equals c? It's like complex everywhere, right? Does the curve stay inside? Yes, because the curve is just a line from 0 to I pi. That's inside the complex, because I is complex. And 0 is complex as well, so 0 plus 0 I. So we have this, and then computing it, get -2. So my first question for this specific thing, well, z equals it, right? Well, my question is, how, like, why is this important? U equals c. And then when we take the derivative of this and we plug it into f of z, because this is equal to this, then we know that f of z is just exponent z. And then to apply the fundamental theorem of calculus, we do this instead of the f prime. So we just want to check, like, why do we look at the why do we even have to solve for the lowercase f of z? Okay. Okay, so let's go over the first. So why do we have to know that u equals c? And what else? Why do we solve for f of z if we just need to plug in the fundamental theorem of complex calculus into the f of z? Do we just do that so we have to know if it's entire everywhere? Can't we just tell since it's an exponent? And also, can you explain what is and isn't entire everywhere? Like, I know log is entire everywhere, but the real axis, the negative axis. So, yeah, make a chart or something. So first, what the problem is really testing is not can you compute e to the I pi, because we already know how to do that, right? That's not really complex variables. That's just calculus. So they're trying to test, do you know when you're allowed to use the fundamental theorem of complex calculus? So that's why they force you to find u and check if this is this, even though it feels obvious here. So why do we need to say u is complex? Because the theorem has a condition. It only works if f is analytic on an open set containing the curve. So it has to contain the curve. So you're proving this function works everywhere. Therefore, your curve is definitely safe. In this problem, f of z equals e to the z plus 2 plus I. Exponentials are analytic everywhere. So mu is equal to complex number using the complex plane. So the real testing here is, can we use the fundamental theorem of complex calculus? And we need to see if f is analytic on an open set. containing the curve. So this includes things like exponents, because exponents are analytic everywhere. Another thing is polynomials. Conceptually, you can just tell that exponents are analytic everywhere, but in math, you still need to state the domain explicitly, as in U is in the complex plane or the domain. But because later problems like log, square root will break this, so the step is about discipline, not difficulty. So why do we check if f prime z, capital F prime z is equal to f of z? Because that's what the fundamental theorem of calculus requires, right? That, you know, we need to check these two things. If it's analytic everywhere, and if f capital F prime z is equal to lowercase f of z. So in this problem, the derivative is the same. Constants are 0. So yeah, you have to check the antiderivatives if it exists and if it works on the region, if the curve stays inside. The problem is easy because all three are trivially true. Now your bigger confusion is entire versus not entire. You said I know log is entire everywhere but the negative real axis. That's actually not correct. It's important, right? When entire actually means entire everywhere. I said but the negative real axis. I didn't say it's entire. Okay, I'm just, yeah, trying to explain. Anyway, so entire functions are sine, cosine, polynomial. Okay, I said exponents and polynomials, but it's also good to know that sine, cosine are also part of this and combination of these. So yeah, sine z, cosine z. So those are the three main uh entire everywhere analytic easy stuff to work with when doing these sort of problems. Rational functions are not entire everywhere because if the denominator were to be 0, it wouldn't work. Or over here, if it were 1, then yeah, the rational functions are not entire. So these are the dangers. I have to write down. Not entire if rational. Like 1 over z, etc. Logs. I already knew that. Logs. Like log of z. It's analytic everywhere except the negative real axis. That's what I said. Alright, and then square root. Square roots are multi-valued, so they need a branch cut. So there's some part of it where it's not analytic if it's a square root. So key correction to your thinking, said log is it's not entire at all. Okay, yeah. Sorry about the wording. It's only analytic on a restricted domain, a slit plane. The distinction mattered a lot later. What is this, an English class? A slit plane. That's what I mean. That's what I meant. Okay, intuition. This will help you remember. Entire function. Smooth everywhere. No breaks, no holes, no ambiguity. Not entire function. Something goes wrong somewhere. Division by 0. Multi-value behavior. Log square root. So back to the problem. Exponential. Entire. Safe everywhere. So use the complex plane. Curve is inside. But how do you know the curve is inside? I know that analytic everywhere means that the curve is the curve is inside. But what's the curve that we're talking about? It's fine. We don't have to ask more questions than we need to. All right, next question. So 2.16.2, the problem is now we're dealing with where the domain, the function is rational. So this is the danger zone, right? It's not entire. This is where the denominator can be equal to 0. If we have, let's say, 1 for z, or negative I don't know, Why is my voice cracking? I'm not going through puberty. I'm not even a guy. Anyways, so this is what we have. This is a Mobius transformation here. Mobius. So what are we trying to decide? Is it really an antiderivative? Where is it valid? This is the tricky part now. Does the curve stay in the region? If yes, then use the fundamental theorem of calculus. So I don't think we can use it, but let's see. So what is our f of z here? All right, this is 2.16.2. I'll just submit this afterwards. So, man, I'm actually really nervous. But let's keep going. 1 minus z squared dz. Again, c equals to it here. T being in the interval of 0 to infinity. So we have that f of z is equal to half log 1 plus z over 1 minus z, right? Because we have here how do you graph this? How do you graph this in the complex plane? The iPod is just 1 on the complex axis, right? On the y-axis, because the y-axis is imaginary, so you multiply it by pi. Pi on the, you know, the radius, the angle is like just one quadrant. So that's how you graph it. So that makes sense how they graph that, but I'm not so sure. I'm not so confident in that. If it's not easy like this question, it's gonna be hard to do. But let's keep going. So they give us this f of z is half log of that, okay? So well, okay. So the principal logarithm is analytic on the slate plane everywhere but the negative real axis. So f of z is analytic on the pre-image of the slate plane and the Mobius transformation w equals what they gave for f of z, which is a double slate plane u with slate from infinity into the negative 1 and 1 along the real axis. The curve c is ray from 0 to infinity along the positive imaginary axis, which lies um in u by the chain rule and the quotient rule. So this is us trying to take the derivative here, right? But I think what they're doing here is multiplying it by the quotient rule or the chain rule. So yeah, I don't know where to get that negative one from. But let's see how they explain it here. Is this so we're gonna see if is this a real antiderivative? Where is it valid? Like where is it analytic? And does the curve stay in that region? Only then can we use the fundamental theorem of calculus here. So we have to differentiate it now. Use the chain rule and the quotient rule. So they didn't go over how to do the chain rule and the quotient rule. It's just saying like they did it here but I need a longer explanation, bro. Like, what is all this? Anyways, can you go over the differentiation, please? So I know the chain rule and the quotient rule, but like I still need to brush up on it. It's been a while. So GZ, where did GZ come from? G of Z. So they said that f of z is this, right? We're trying to find f prime z, the derivative of what's written over here, which is half log of this. So where did GZ come from? Like, what? You don't need to memorize all the algebra. Instead, the key pattern, a log of anything, looks like 1 over the x. The x being 1 minus c squared. So it's like the denominator squared. Where people mess up, forgetting chain rule, messing up the signs. I'm not at that place to use shortcuts at the moment. But we'll multiply it by half at the end. Okay, so we're just trying to focus on the log part here. So forget about half here. We're trying to differentiate this part 1 plus z over 1 minus z. So the chain rule means that you multiply the inside, the derivative of the inside, by the derivative of the outside. That's why it's a chain, right? So the inside is the derivative of the ratio here. So the quotient rule is this. So we have f prime g plus g prime f g prime squared. No, there's a minus. It's not product rule. See, I don't even remember the quotient rule anymore. But the denominator is v, right? So we have f prime g minus f g prime over g prime, no, over g squared. There's no prime at the bottom. So that's a little refresher with the quotient rule. Hi, do you remember me? I think I do. I mean, I don't remember what I remember about you, but I definitely remember it being quite a long time. But yeah, I remember your cat looks a lot like mine. So yeah, welcome back to the stream. How's it going? Yeah, I think I do remember you. I'm Goofy. Yeah. Hello, Oliver, Jimenez. Welcome to the stream. How's it going? So we're just applying chain rule here, and we're gonna have to apply the quotient. Actually, no, this is not the chain rule. This is the quotient rule for the chain rule. And then we're going to do the derivative of the outside of the log and multiply it by half in the end to get the derivative of the integral f of z to check if it's, we could use the fundamental theorem of complex calculus. So we could answer if this right here works for the fundamental theorem of calculus. Anyways, I gotta go. Sorry, bye. Have fun. All right. Thanks for tuning in, the goofy, and have a good rest of your day. But how's it going, Oliver? What grade are you in? Um, I don't really want to say. I know that's kind of weird that I'm doing all this and then I don't want to say. But yeah, I guess I'm just kind of shy of my age. But it's just math. It's like higher level math. Okay. Sorry, Oliver. But yeah, you could tell me about yourself. Like, what grade are you in? If this is familiar or not. Probably isn't, because most people don't do this level of math. It's hard though. Like, I got a F on my um, first exam. I thought he just didn't grade it. I was like, oh, my grade's gonna go higher after this. But it stayed at a 45, like, overall. So imagine. How am I supposed to pass? Like, it's not like the lowest passing grade is 60 anymore. Like, for other colleges, it is. But for my one, no. Make it like the standard grading system where you have to get a C or above to pass. So I'm actually cooked. 8th grade? Awesome. But yeah, I think 8th graders learn calculus too, right? Or not most 8th graders, but some of them. But yeah. So, if you know anything about derivatives, have you heard of derivatives? Yes, we do. Awesome, awesome. So you know what the chain rule is and the quotient rule is. So this shouldn't look too bad to you. How to do it. But if we take f prime for the numerator, just get 1, right? Because the constant goes to 0 and variables go to 1. So 1 times g, which is the denominator, 1 minus c, minus f, which is 1 plus c, times the derivative of the denominator, which is negative 1. So that's for the numerator. And the denominator is just 1 minus c times 1 minus z. So I think we could just like cross cancel a little bit on the bottom there. So we get 1 minus, well, this turns into negative 1, this turns into negative z. And then to spread the negative back, we just get 1 minus 1 plus z. So that's just z over 1 minus z. So that equals 2, right? Simplify the numerator. This is bad. I got something completely different. Why did I get something so different? Let's see. So trying to find the differential of this. I got this part right. Uh-huh. So simplifying the numerator, you get 1 minus c minus 1 plus z minus 1. So be careful here. So maybe that's where I messed up. 1 plus z minus 1 is negative 1 minus c. So if you're subtracting, then you get the positive because you're multiplying it by the negative, right? So you get 1 minus c plus that. But I just canceled it from the denominator. But you're not supposed to do that. So let's just leave that. Whatever. 1 minus c plus 1 plus c is equal to 2. for the numerator. And the denominator stays 1 minus c squared. But that's so weird. Like, I just cross canceled it. Like, it's fine. Hi, yo, Grace Kershaw. How's it going? And Rio's Brother Gaming. Welcome back to the stream. How's it going? I'm just kind of confused how I got something way different. Even though all my steps are correct, I did 1 minus c minus negative 1 minus c times negative 1 over 1 minus c 1 minus c. What I did was cancel that out. I get 1 minus minus, so that just goes to negative 1 minus c. Oh no. That's so confusing. Oh my god. Assalamu alaikum everyone. Wa alaikum assalam wa rahmatullahi wa barakatuh, Coco. How's it going? And Grace Kershaw. Welcome. Yeah, have you taken calculus, Coco? Because I feel like you're a older viewer, right? I don't know. Probably assuming. Forgot your exact age. You're like 20, right? Trying to see how I did this, but I forgot. Like the steps are so unclear, so no. So I'm spending way too much time on this. So you get 2 plus z over 1 minus z. But how does that just like simplify to 2? But it's better not to just like cross cancel that way. I don't know. So weird. How do you get something different? Like, I'm 20 and yeah, I've completed calculus, but not fully. Oh, okay. Like, how do you complete it without doing it fully? This is so confusing. It's confusing because I got something way different than what they got. They got 2 here, which I could understand how they did it by their way. While I was doing step 4, I cross cancelled 1 minus c from the top and bottom and got the result of 2 minus 2 plus z over 1 minus z. So this is where things went wrong. It said you cross cancel one minus you got something like this. Why the cancellation is not allowed. You can only cancel factor when they multiply, not when they're part of the sum or difference. That's so stupid. Why did I do that? It's illegal. It's literally the stupidest mistake ever. Man, that's so true. I can't believe I made a mistake like that. It's illegal. May Allah help me, man. That was the dumbest mistake ever. I mean, I've ever made. Top 10. My professors these days, like, what the hell? Alright, so now I know why it goes to 2. Can't cross cancel from the top and bottom. That's too tempting, I know. You just want to cancel everything, make it easy. But it's equal to 2. We take the chain rule doing this. Of this. So we have that times 2. But what is the derivative of log of this? So g prime z is 2 over 1 minus z squared. Because g of z is this. But where's the denominator coming from? Where it was 1 minus z squared from? Oh, 2 is the numerator. Dang. Yeah, I forgot that. The g squared part is 1 minus z squared. So that equals g prime z. That's just the, the derivative of the inside here. We still have to do the log part. So plug it into the chain rule. We have log of g prime z equals to this, right? G prime z is this times 1 over gz. So the log of anything is 1 over x, like the derivative of log. So we have to multiply this by 1 over 1 plus c, 1 minus c. Which, if you think about it, if you multiply it by 1 minus c, the top and bottom, you get 1 minus c over 1 plus c. And you continue multiplying it by 1 minus c squared. So that goes away. The exponent on the bottom, that goes away. But I'm not doing it in the right order. Does it matter in which order you multiply it? I don't think so. 2 over 1 plus c, 1 minus c. That should be our answer. And then you multiply by half because from the beginning, that's where we left it. You should not forget that. Which is equal to the same thing, 1 minus c squared. Wow. And it equals to the function here. So after all that quotient rule, chain rule, we get that f prime z is equal to f of z. Awesome. So what you should actually remember is you don't need to memorize all that. I would remember that 1 minus c times 1 plus z is equal to 1 minus z squared. These are the small rules that only real mathematicians remember. Anyways, so yeah, so going back to when they assumed that we knew how to differentiate properly like that. They overestimated me. That was just step 1, which to check that. Step 2, where is it valid? Remember, log is not entire, so it's not analytic on the negative real axis. So when is the expression valid? We need this not to equal, not to be part of the negative real axis. So we do the Mobius translation, or the Mobius transformation. We're avoiding values where the expression becomes a negative real number. So when would it become a negative real number? If z or z are like, if the denominator z is greater than 1 or 0 or greater, and if the numerator z is less than 1 or like less than 0. So after mapping everything out, it summarizes the domain becomes the complex plane minus 2 slits along the real axis at z equals 1 and z equals negative 1. So the u equals the plane with cuts at negative 1 and 1. So because if this was negative 1, it'd be at 0. If this were 1, it'd be at 0. So we're going to avoid when z equals to 1 and negative 1. So these are the bad points, right? The denominator is equal to z, 0 when z equals 1. So the log breaks, creating the branch cuts. Just, yeah. Does the curve stay inside u? Curve is equals it, pure imaginary axis. So anything multiplying by I is the y-axis. So it looks like starting at 0, going up straight. Yeah, because it's not negative, right? It's just like that. So this path never hits z equals 1 or z equals negative 1. So the curve stays inside u. Wow. But we know t is positive, right? Because they said that t is between 0 and infinity, right? Up here. T is within that range. So it has to be in that positive y-axis, imaginary axis. So with that being said, all the points are checked, that it's analytic on the interval that we have been given, and that the derivative of the capital F is equal to the regular f of z. So once these two are checked, so it's important when z equals to 0. So it could be just 0 or multiplying it or subtracting by anything that makes it 0. So in this situation, we have that rational, right? So z squared could be 1 or negative 1. Any those two squared gives you 0 for the denominator. So u equals to c. With cuts at negative 1 and 1. So the denominator, okay, so does the curve stay inside? It does. The curve does stay inside. With t equaling these things, right? It never hits negative 1 or 1. So we apply fundamental theorem of complex calculus. And what do we get when we do that? So we have f of that minus f of this. What was f? F of z was half log of that. And we have 0 and infinity. So this part is supposed to be easy. I think the complex, the fundamental theorem of calculus is pretty simple. But no, that part is hard. Because doing f of ib, not infinity, just ib. End and start. So the start is 0, right? That's a, and the b in the top. So f of 0 is half times log 1 equals to 0. Why is it log 1? Why not log 0? It's log of 0. Oh, I guess because if you have 0 here and 0 here, then it becomes log 1. Okay, okay. So f of 0, this is half log 1. And log 1 is equal to 0. What is log 1? Okay, so that equals to 0. How did I forget that? So the end is I times infinity. B equals, we compute the limit when b equals to infinity f times ib. So we're not going to put infinity, right? It's going to put ib. They simplify it to I pi over 2. I pi over 2? How do you get that simplification? Yo, Polarius, hello, welcome to the stream. How's it going? Look, thank you so much. I'm good. I'm just really stressed about this um thing where, yeah, it's pretty complicated. But how do you get it I pi 2? Okay, so they get it like this. So they put IB where B goes to infinity, right? Because in the y-axis. So if you plug it IB into Z, then you get, alright, sorry about that. Um, alright, sorry about that. Um, yeah. It's important to remember certain rules like log 1 goes to 0, or that 1 minus z, 1 plus z equal to 1 minus z squared, and things like, I don't know what else. That you can't 1 minus z here plus 1 over 1 minus z times 1 minus z. You can't, that's illegal. These are simple things. You should remember these things. It's hard to. Anyways, so I don't know how the top becomes squared all of a sudden. 1 plus b squared. Like how they do that? Somebody explain. Where did squaring come from? Did they just square the top and the bottom? Hmm. And then they took the ln plus I arg. I would need explain step 5 and no, not that, not that. I'm talking fundamental theorem about the complex calculus. Multiply top and bottom by 1 plus IB. Then get squared over here. Okay, so that's what they did. They didn't just square the whole thing. They multiplied 1 plus IB. Alright, so this helps because you can separate log into ln and I arg, and then take the limit becoming 1, so the ln of 1 becomes 0, and then plus I arg of this is just pi. That's so confusing. Yo, Thunder97, welcome back to the stream. How's it going? I'm so, I'm so anxious because we have a quiz tomorrow, right? And we're supposed to practice the homework, the GCR 8, which I'm doing right now. But Koshigar saw everything goes to 0. Like, that's supposed to be really simple. For the given contour integral, check if the hypotheses apply, and if they do, apply it to the compute an integral. Okay, so that's what I'm doing right now. This one, I'm doing this right now. And then there's 2 other things. It's not too hard. It's not the end of the world. I just kind of have the camera pointed here because our cat's in the back. Good for engagement, but also kind of limits how much of the screen you can see. Which also works for the best because, yeah. So this is just problem 2. How many problems do we have? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, 10 problems, not too bad. I thought it would never end. So we're in problem 2 out of 10. So we're making progress. We studied for 1 hour. Probably need to study for more than 10 hours at this point. But it's okay. We'll get there, inshallah. Yeah, so far it's good to know like where we're at least. But yeah. After this question, I think I might have to leave because my mom needs me for an errand. And I do need to pray and answer. But I have to understand like where the ln plus IR comes from. I know that was a formula for something. Probably like I forgot by now. Magnitude. Oh, wait, no. Where'd the ln plus IR come from? Where did the ln plus I arg come from? Like, what formula was that for? I forgot. I remember memorizing the formula, I just forgot where it came from. Foundational piece. If you don't have a solid, the log problem feels random. Oh, okay, so that's log. Oh my god. I was just asking. The answer is in plain sight. It's not random. I remember this formula. I just forgot that it was associated with log z. Got a lot of things. If I would remember everything that I've ever learned, this would be a piece of cake. But we're humans, right? We need to practice every single day. But there's no reason to practice if we don't have a quiz coming, right? It's not like it's my passion. But yeah. So log 1 times half goes to 0. And now we're doing f of I infinity. Well, I is important, right? Because we're taking the limit as b goes to infinity. So then we get IB. F times IB, which equals to half log of 1 plus IB over 1 minus IB. So the formula for log z is equal to what was it? ln magnitude z plus I arg z, right? But we want to simplify z as best as we can. So we multiply the top and bottom by 1 plus IB. 1 plus IB, that's just 1. But it does give us something easier to work with. Just 1 minus IB squared, right? It's 1 plus IB squared. And then for the top is... No, it's not the whole thing. It's just 1 plus B squared. The top is 1 plus B. All of it is squared. It's like one thing after the other. It's like too much to handle sometimes. So I'm gonna forget a lot of stuff, but the more we practice it, the more